Not to be redundant, but thank you very much, Henry. Thank you, Krishna, for having me here. It's an honor. And also thank you for the audience for being here on Friday morning and being so interactive. I mean, this is one of the most interactive audiences I've ever seen. So great. Today I will talk about sparsity and privacy in distributed matrix multiplication. We've seen some talks on coded computation, and also Emina talked about also related problems. The application, so application-driven coding theory workshop, right? The application is that so data is generated daily and it's analyzed, and it's a tremendous amount of data, and we've seen that any saving we have, so Rashmi said even 10% of saving saves a lot, and also Aditya was so happy about sparsity. So any saving we can have is important. And what I want to focus on today is privacy, data privacy in the era of analyzing sensitive data, and sparsity or efficiency in distributed learning. Now, when we say distributed learning, many concepts pop up in mind. And the most frequently mentioned settings are the following. We have the main node worker setting, where one node has tremendous amount of private data and wants to run a machine learning algorithm on it. It has access to some worker nodes. It offloads the computation to the nodes. They run the computation and return. And that's the focus of this talk. The other settings are federated learning and decentralized learning. The main contrast is that in those settings, there are many users. Each of them has their own data, and they want to run a collaborative machine learning algorithm on the union of the data. So in federated learning, we have a federator orchestrating this learning process. In decentralized, just the users they talk about. They collaborate. Some of the techniques I'm going to talk about today, they apply here, but we have not looked at this, so that's one of the open problems. Okay, so what are the main challenges? Many of you here that worked on those challenges, and so the first one is stragglers, of course, slow or unresponsive nodes, heterogeneity. So in heterogeneity, I mean that the workers can have different speeds. So some of them may be stragglers, but some of them may be very, very fast, and you want to accommodate that, and maybe time varying, right? So for example, I think Krishna here, you have this factored LT code, right, where you want to do distributed matrix multiplication, matrix multiplication, and you want to do it inside sort of a rateless fashion, so you want a fountain code. That can accommodate for heterogeneity. The other problem is privacy. So how can we assign computation to the workers on private data but maintain privacy when the workers collude? Many of you, I think, worked on this as well. Security against malicious workers, and efficiency. So one wants to reduce the overall compute time. One wants to reduce the complexity of the computation and the workers, and so on and so forth. I'm happy to talk about all those offline, but today I'll keep it simple, and I'll talk about one less mature problem that we started a year ago, and it's very interesting in my opinion, and I think there are many ways to extend on this. And this problem is going to be focusing on efficiency in the computation, in the sense that the data of the main node is sparse matrices, combined with privacy and straggler tolerance. Okay, that will be the focus. So the system will reduce from this figure, this populated figure, it will reduce to this figure. The system is as follows. I have a main node, and that main node had two matrices, A and B. Those matrices, and wants to multiply them together through the help of the workers. Those matrices are sparse, and my sparsity is defined as follows. The entries of, I'm going to talk about A mostly, but everything I do to the matrix A, I also do to the matrix B. So no loss of generality here. So I'm going to say that the entries of A, they have the same distribution, so IID. And they're distributed as follows. They are 0 with a certain probability SA. That's going to be the sparsity of the matrix. And they are non-zero. They can take any value, any non-zero value with the same probability. It's 1 minus SA divided by Q minus 1. My matrix is in FQ, the entries. That's the sparsity of the matrix. Privacy, I'm going to focus on information theoretic privacy of both matrices A and B. But I'm going to assume that the workers do not collude. So each worker, they just take whatever they observe and on their own try to learn something about the matrices. Okay, no collusion. Good. Stragglers, we all know what they are. And the efficiency, so I'm going to measure efficiency by the sparsity of the matrices that's assigned to the workers. So again, linking back to Aditya yesterday, You were considering matrices of 98% sparsity, and then if you do some codes, you reduce sparsity significantly. I'm going to show you that if you do also privacy, you destroy sparsity, right? There's no hope. So I'm going to allude to that. Just next slide. So what I'm after a coding scheme that encodes those A and B into tasks, send them to the workers, and satisfy some privacy constraints, best sparsity I can get for the sparsity constraint, and straggler tolerance. That's what I'm after. Great. So here's the outline of what's going to come next. I'm going to tell you about the interplay of sparsity and information theoretic privacy. Maybe you directly thought of this, and I'm going to confirm your thoughts. And then I'm going to show you if I have a desired sparsity guarantee, what is the trade-off? What privacy guarantees can I give? And the schemes, so one-time pad and Shamir secret sharing, I'm going to define those. And then some numerical observations that will hopefully give you some thoughts on how to expand open problems. And conclude. Of course, in conclusion, I'm hiding to unsolicited advertisement, just so you know, but it's there. Okay. So, yeah, you know this. Okay, information theoretic privacy is that the observation of the workers has to be statistically independent from the data. Is like mutual information is 0. The assumption is that the adversary has an unbounded computation power, but I have to put a limit on the colluding workers. In this talk is 1. Okay. But some variations of this that we know in the community is, so this is the perfect privacy, right? If I want the mutual information to be 0, but then I can relax it. It's strong information theoretic privacy if this mutual information is epsilon that goes to 0 is block length, here the size of the matrices. Or I'm going to call it weak information theoretic privacy if the mutual information is epsilon and it's constant. Okay, so basically in this talk, I'll focus on this one and this one. In my coding scheme, the tasks assigned to the workers are going to be of this form. The matrix A and B, they are going to be mapped to polynomials, right? Secret sharing, basically. And the polynomial is going to have a form of A plus X times R. R is a random matrix drawn from the field in which A lives. And for B, it's going to be B plus X times S. Also, S is a random matrix drawn from the same field in which B lives. I'm going to assign to the workers evaluations of those polynomials. They'll multiply the evaluations and give me the results, to the main node. Right? And the multiplication of those polynomials is a polynomial that has the 0 coefficient is A times B is basically what I want. So I have to assign enough. I have stragglers. Now, everything is finite field. Yeah. I need finite fields. Right. Okay. So now what is the privacy guarantee that I can give? It's going to depend on how R and S are drawn. Right? And the traditional way to do this is to say R and S are independent and IID, like independently and uniformly distributed from the field, so that I can guarantee the strongest privacy guarantees. Bad news, if you insist on this, there's no sparsity. Let's look at this in schematic form. What am I doing in secret sharing? I'm taking A as the input matrix, put it in secret sharing. Those are just the parameters. N shares, K is the recovery threshold, Z is the collusion parameter. So I'll focus on N to 1. It requires me to generate one random matrix, and it's going to output those shares. If this is uniform at random from the field, independent from A, those shares are as well uniform, and that's why privacy holds. Now we go to the application. In many, many, many algorithms, machine learning data, blah, they are sparse matrices. Let's say, Aditya's example, you have sparse matrix, a matrix that only has 2% of non-zero entries. You do this, you have, let's take 1 over Q of the entries are 0, right? And if you take Q to be large enough, you're done. And the question, can we do better? Can we have some sparse output here? And the answer is, if you want information theoretic privacy, then no. If you're happy to relax it, then there's something we can do. Yes, Rudiger.
So right now you're hiding it by adding stuff, right?
Right.
What about if you just edit random permutations, both for row and column?
Would work, and I will actually need this one. That's a good idea. The reason we didn't, we just want to see if you add like information theoretic privacy. Yeah. But you can. And in the last slide, the numerical observation, I'll show you that you may need this on top of what we're doing. Good.
Are you insisting that you have the best straggler tolerance when you say this? And even if you relax the straggler tolerance, you're saying that you cannot get privacy?
even if you relax straggler. If you forget about, so here you can forget about straggler, okay? Just take 2. Okay. You still cannot do anything because this is still very, very dense. If you want straggler, so what I will show you next is the number of shares that you want will worsen the sparsity you can get. Okay, so the fundamental trade-off is as follows. Information theoretic privacy and sparsity, they cannot coexist. To make them coexist, you relax a little bit from privacy. If you want stragglers and same sparsity, you have to relax even more. That's how it's going. So here's the dilemma that if you fix k is 2 and z is 1 in secret sharing, we can prove it theoretically that perfect information theoretic privacy can be achieved if and only if the random matrix is drawn IID. And here's what the graph, it's what it looks like. So I call it relative leakage, is the normalized mutual information between the share A plus XR and A divided by H of A. If we don't want sparsity, so we're here, that's so we can show this is a convex optimization problem, and the global optimizer is at 1 over Q. So basically R is uniform. And then once we want to more sparsity, once we move from 1 over Q, we have to have leakage. It has to be non-zero. And the more sparsity we want, the more leakage we will need. And there's another dimension. I'll get back to this. Okay. Questions? So what is the main idea? The main idea is very counterintuitive in my opinion, because when we say privacy, we say I want to mix the data with random numbers that are independent from the data. But here, because I want sparsity, I want the random number to be dependent on the data, to maintain zeros. I want to have those zeros. And the challenge becomes, how can I design the randomness dependently on A to guarantee both sparsity and privacy? And to give you a small example, I'm going to use the whiteboard. Is that fine? Okay. So the small example is I want a secret sharing scheme with 2 shares. The first share is R, and the second share is A plus R. So just 2 shares. And my input matrix A looks something like this. Let's just take it to be 3 by 3. And has 0, 0, 0, some non-zero element here, 0, 0. Okay. Now, how do I design R so that R and A plus R, they are both sparse, but also don't reveal too much? That's the question. And the answer is, because I assume this is A, do you want to think a little bit about that? What are the principles? That's one idea, but then if I do that and I reveal R,
you know where the non-zero entries are, right?
Right. And you may also know the value if you specify the value. So the first idea that Aditya came up with is I want to hide the non-zero values, and that's legitimate. But sometimes also the position matters, and also I don't want R to be a multiple of A, minus A, for example. So that's the first idea. So design R dependent on where those guys are. Sure. What else?
Permute the matrix.
I'm going to get to that in the end. No, don't permute, not yet.
Few more non-zeros.
Sorry?
There's a few. Flip a few more non-zeros.
Yeah. Flip a few non-zeros randomly, and the zeros flip them to the non-zero flip them to 0, but also don't always flip them. That's going to be the idea. So I'm going to have 3 parameters, 3 probabilities, so that this will happen. But because I assume everything is IID, I'm just going to look at one entry in A, and whatever design I do here, I'm going to repeat it for every single entry. Now that you have this graph in mind, hopefully this will make sense. I'm going to design the random matrix R based on A. I'm going to look at A, and I'm going to say the following. If the entry, ij entry of A is 0, then the ij entry of R is going to be 0 with probability P1. That's parameter. It's going to tell me how many zeros I inherit from A into R. And it's non-zero with some probability. Okay, I don't care. Because by assumption, my entries of A are uniform over non-zeros, I'm going to do this. Okay. And if it's non-zero, and if A is non-zero, then I either keep a 0 with some probability, P2, or I choose minus A with some probability P3. So I turn off non-zeros in A to zeros arbitrarily, but not always. And with some probability 1 minus those guys, Q minus 2 is something else. Okay, that's the construction we came up with, and the motivation behind choosing those, you can still choose them whatever you want, right? But the motivation for choosing them uniform over all the unimportant entries is because we assume that the entries of A are uniform over the non-zeros. So that's what I explained now. So
Since you are interested in the mutual information between what the worker sees and the private data, does the worker know the prior on this matrix is sparse, or the worker does not?
the worker would know the prior, it would know the sparsity of the data, and it would also know the scheme, how I generate the random numbers. So, okay, so this parameter, it maintains sparsity of R, I ID non-zero values, this I keep non-zero in A plus R, this has sparsity in A plus R, right? And this I ID non-zero, kind of to hide what's happening. So, and you can show that the sparsity of the shares R and A plus R. This is the one-time pad, by the way, so just R and A plus R, okay? So the sparsity is gonna be this one, P1S plus P21 minus S, and this one. So the sparsity is increasing in P1. So you may think I wanna increase P1, but so does the leakage, right? The information leakage is gonna increase with P1. Let's take an example where I just set P1 to be 1. And then so every 0 I inherited here. So whenever I see a 0 in R, I know that this was a 0 in A. And I could also set this one to 1 and everything else to 0. So basically R is minus A. So if I reveal R, it's going to reveal everything. But A plus R reveals nothing. So I have to be careful how to choose that. And the way I'm going to do it is I'm going to tell you, fix a desired sparsity. Tell me I want this much sparsity in the shares. What is the best privacy guarantee I can give you? It becomes an optimization problem in those P1. And it looks like this. You fix the sparsity. You write the leakage as the, what do you want? You want to optimize the leakage, minimize the mutual information, write it as the KL divergence. It becomes a convex optimization in those P1, P2, P3. Solve it, you're done. Okay. That's what it is. Now, this note here is to tell you, so I focus my attention on construction of this form. But what if you don't want those to be uniform? What if you allow yourself to play around? For small values of Q, we made the optimization for all possible constructions of R, and the result was you should choose those uniform. Okay, so just for small numbers. And then the results will give you the optimal questions, because now I want to generalize to more shares.
So when you say optimal privacy guarantee, that means what?
It means fix the desired sparsity and get the P1, P2, P3 that minimize the leakage, because it's convex optimization.
But do you have is that the best thing to do, or is there
I don't know. I don't have a bound. Okay, and then that's the reason why I mentioned the numerical thing. So if you run the optimization problem for any possible code construction, you get what I suggested. Okay. But we don't have bounds, nothing, so that's open. And now you can take your scheme, right? This partial straggler, and then how do you do this in distributed computing? You just generate the shares, and then you can give them any way you want, cyclic shift, or to maintain partial straggler. Okay, so this is just one naive way to distribute. Say you have 4 workers, you give A plus R to 2 of them, and R to 2 of them, and you can also chunk A plus R and R smaller chunks, and inside whatever. But the nice observation we had here is if there is a wall between those 2 workers and those 2 workers, think of 2 clusters. Like let's say at TUM we have our own computing cluster, and then I want to hire nodes in the cloud. At TUM I partially trust the cluster, so I can leak a little bit. But in the cloud I don't want to leak no information, 0. Okay, what can I do? I can design my P1, P2, P3 to be a constant and equal to each other. Then A plus R leaks nothing about A, nothing, and has some sparsity. R would leak a little bit about A, but still have sparsity. And then I would assign A plus R to the untrusted cluster, and there I can allow full collusion, right? Under some, how do I distribute the matrices? But then in the partially trusted cluster, I leak something, which is fine. All I have to do is just fix the sparsity guarantee, and then I get the leakage. How am I doing on time?
So I'd say maybe 5 minutes.
Okay, sure. Good. So this is now to generalize, like if you want to have more shares and not only fraction repetition and whatever, what can you do? You have to design the same thing basically, but now each share is going to look like A plus XR, and you evaluate at alpha i's. So you fix the alpha i's, and now you decide where to turn zeros, in which share, for which alpha I you want to turn non-zeros to zeros, and for which not. So those becomes the parameters for all alpha I in the set, and you design them, and they run the same optimization. So that's the sparsity of the share. And again, here you can easily see why this is an increasing function in P1, the sparsity, but also the leakage is increasing function. You run, this is the optimization problem, just run Lagrange multiplier, you solve it. The idea is to prove that this is, that minimize the leakage. I'm gonna tell you all the assumptions so that if you wanna think of the problem, what are the assumptions we made? First assumption is that we assume that all the shares must have the same sparsity. This shouldn't be the case. For example, in the two cluster thing, it was not the same. Then we prove that this, under this constraint, if all the sparsity are the same, then the problem is convex optimization. Solve it for the construction that we have. For this setting, we didn't try all numerical possibilities. We stick to our construction and then solve the problem. Okay. Now, now how can you use this in, again, if you want more than 3 shares, or if you want to stick to a small number of shares and do repetition, that's what you can do. Just split the workers into groups, and for each group, you give some of those sparse things. And you can compare to, sorry, this is not clicking. Yeah. Oh. Now you can compare to the mat.dot schemes, right, that Aditya talked about yesterday. So you could do what I'm telling you. You could do the sparse thing, but you could also do the regular polynomial. And what you care about is how much computation is each worker doing, right? So how many non-zero entries they're multiplying. And what you see here is when is our scheme beneficial. So let's look at the setting where we have 1,000 workers, and sigma is the proportion of stragglers. For small number of stragglers, our scheme is beneficial starting if you require the share to have sparsity 0.2. Everything above then, our scheme has less entries, less computation at the workers. But in the regime where the number of stragglers divided by n, say, is between 0.1 and 0.8 or 0.9, then if you want less sparsity of the share, so say less than 0.9, it's better if you use mat.code. They will have less computation. And why is this? Because we do this grouping type of thing. So we can divide the matrix, but division is not too big, and so on and so forth. But if you have less workers or less stragglers, then our scheme becomes beneficial for lower sparsity. Numerical observations. First, the leakage increases with the sparsity. It also increases, here's your question, Krishna, with number of shares, right? So if you have more shares, then you must leak more to guarantee sparsity. That's it. If you increase Q, then the leakage decrease for same sparsity, and this increase of leakage with shares become less significant for large Q. The second observation is for the one-time pad, K is 2, Z is 1, we prove that if the shares have the same sparsity, then it's optimal. It's the less leakage we can get. Once the sparsity of the share deviates, this delta here is how much this difference, then you have higher leakage. Okay. And now we come to Rudiger's question. Okay, this is nice and easy. I assume entries are IID, but what if they are not IID? Here's the drawing where this is a matrix with non-IID matrix, and I apply my scheme to it, and this is the private matrix. Very private, right? Doesn't look so private. And now you can, of course, apply random permutation. Then this is the entry, and this is the privatized matrix. Makes sense. So there's a lot to be discovered. Okay, with that, I conclude. So in summary, we talked about private sparse matrix multiplication. There's a fundamental trade-off. I showed you some solutions optimal in the sense that you minimize like convex optimization under IID entries for the matrix, and we talked about those trade-off privacy with Q and N, and extra care is needed for privacy with for matrices with correlated entries. Many open directions, but of which I want to put on the slide is improve the rate for larger K, improve collusion, and beyond IID entries. Now the advertisement. And Antonio already advertised the workshop, so we have Munich workshop on coding and crypto. Some of you attended previous versions, some of you are attending this time. Another advertisement is hidden here, is that there's another workshop right before this one. So on April 3 to 5 by Gerhard and Gianluigi is on Shannon coding techniques. It would be nice if you are interested and you want to join. You nice to see you in Munich. The other workshop, Eitan already, so this is redundancy now. So the other workshop, Eitan already mentioned. So this is a ISIT satellite workshop. Henry is coordinating. We're organizing this with Eitan, Antonia, and Dave Landsman from DDNA Data Storage Alliance. The contribution, if you want to submit a contribution, we only have posters or talks, no papers. Then deadline is April 15. Here we'll extend the contribution for 1 week if you're interested in contributing something. So the focus is on post-quantum crypto and privacy-preserving machine learning. Okay. Now,
Thank you, Ron. Questions?
Thanks for the nice talk. Are there any proposals that make use of computational assumptions to try to do this more efficiently, or would they all require very heavyweight, like general multi-party computation techniques or something?
let me make sure I understand your question. You're asking if there are some homomorphic encryption schemes that one can use.
Sure, exactly, something like that.
Why not? But if you want fully homomorphic, then maybe the price is high to
Yeah, I
pay.
agree, fully homomorphic, but I guess you need just some sort of additivity, sort of.
Maybe you can get away. I'm not the expert, but maybe you can get away with it.
Yeah, you have to.
I had a question along the line of this random interleaving. So if you have a matrix multiply and you can insert a matrix in the middle, right?
Right.
And then permutation will change the sparsity. How much security does that provide though? Because it's like you have to use the same for the two matrices. If someone else, but you can do it a different one for each worker, right?
So let me make sure I get your question right. I have A and B, right? Two matrices, and I want to multiply them. Now for each matrix, I'm going to use a new random matrix.
Yeah, because I just put permutations in the middle of the arrow, right?
You can put permutation. Yeah. Right. Yeah. Exactly. Do you want to put permutation on A and then on B such that A times permutation times permutation is going to give you a result? That'll be fine. But then if the workers can invert the permutation, then basically
The workers just see the permuted version.
yeah. They don't know what to look for, but yeah.
Yeah, I guess it's hard to, somehow you have to come up with what's the difference between the values and the positions. Because you are going to see the values, you're going to see the distribution of the non-strategies regardless.
True. If you do only permutation. Yeah, maybe the advantage you get is you hide some of the values.
All right, thank you. Before you think it's time for coffee, I remind you that